This is our second session. We're going to be looking at secondary math here today. And we have Alex Eden, who's New Frontier School Board consultant, math teacher as well. And he led us through the elementary session, which was a really great one. We had a great amount of learning and a lot of aha moments, I would say. So we will carry this aha moment thing forward, and Alex is going to walk us through math ideas, concepts, and then we're going to look at a couple of tools as well. Hey, Sean. And we'll have
Hi,
an
everyone.
idea. We're great. We're doing great. We're just getting started here, so you haven't missed anything yet. Um, And we'll look at a little digit. We're going to look at Desmos too. Hey, Alex, I think that was one of them that we were going to look at, the tool that we had for today that will kind of seep in a bit of tech in there as well. So we will run probably for about 45 minutes. If you guys have any questions, we'll have lots of time. So feel free to either dump them in the chat or you can ask them at the end. We will send out the recording and his presentation tomorrow. So if you can just listen really and chill and enjoy and really focus in on what's being said. And that is that. So thanks, Alex, again for coming and doing this with us. We really love the elementary session and the high school session. We never do anything for high school math, so here we go. Boom, it's getting happening. So thanks for joining us, guys, today. It's good to see a few of you here with us today, but we'll be sending it to everybody that registers as well. So without anything further, Alex, take it away.
Thank you very much for having me today. I really appreciate it. Start by sharing my screen so that everybody can see exactly what I've prepared for you today and see it right now on your screens. Can I get a thumbs up to confirm that we see it? Perfect. So, as you saw from the titles, today we're going to be looking at thinking routines, notably the Notice and Wonder activities from the National Council of Teachers of Mathematics in order to get our students to do meaningful mathematical discourse. Now, that's a big title. It's got a lot of information in there. And right here on the screen, we actually have a visual prompt, which is the New Frontier School Board logo. And what we could do with this with our students is ask them, what do you notice and what do you wonder? And our students will come up with a lot of interesting answers. So for example, some students in high school might say, ooh, I noticed some curves. I wonder if they're parabolas. I wonder if I have to use my conics because they're actually horizontal parabolas. Or they might look at the star and they might say, ooh, I wonder what the interior angles might measure. Or I wonder what the exterior angles might measure. And then they might come up with a question. Well, how can I calculate those angles? What would lead me to find the equation of those curves? And that's what we want. We want our students talking, getting to know each other, and learning from each other. The idea of establishing a routine that supports thinking is not something new. These are ideas promoted by Garfield G. Newman when we're talking about critical thinking. And he really promotes this idea of a thinking routine because it allows for classroom discussions, which means posing purposeful questions. It allows students time to reflect, to learn alone and with others, to think about their answers before they respond. It also allows students to explore ideas, to try out solutions, to revise, and even start anew when their initial ideas don't work out. All of these are critical parts towards problem solving and becoming mathematical thinkers. The idea of using the Notice and Wonder activities is interesting because they encourage a means of having a mathematical discourse amongst the students. We're putting the students in teams so that they're actually comfortable working together and they exchange ideas and there's a respect, a cordiality between them. Intellectual curiosity, critical thinking. It prompts the students to pose questions that they might not necessarily ask in an everyday classroom. It's a different pedagogical approach, and I won't deny, at the beginning it might take more time, But once it becomes a routine, it'll go faster and faster and faster, and your students will benefit. There's another reason for for establishing thinking routines, sorry. We want to question these students. We want to see what they observe. We want to see what they wonder. We want to learn from them also, and we want them to help develop their mathematical identities and to make connections in terms of mathematics, in terms of what they see. Garfield G. Newman actually proposes that there are 6 forms of critical thinking tasks. It could be a task, a critique the piece task, a judge the better or best task, a rework the piece task, a perform to specs task, or even a design to specs task. In the case of the notice and wonder activities, what we're really looking at is a decode the puzzle. We're asking the students to think about that visual prompt in a different way than they're accustomed to looking at it. We're asking them to come up with solutions, explanations, interpretations of what that picture might be showing. Back in 2014, the Principles to Action Ensuring Mathematical Success for All was published by the National Council of Mathematics, the National Council of Teachers of Mathematics. A book of about 150 pages, we propose 8 different mathematic teaching practices that you can see on the screen over here. Establishing mathematical goals to focus learning, implement tasks that promote reasoning and problem solving, use and connect mathematical representations, facilitate meaningful mathematical discourse, pose purposeful questions, build procedural fluency from conceptual understanding, support productive struggle in learning mathematics, and elicit the use of student thinking. Well, today we're really going to focus on 3 of these different mathematic teaching practices, notably the idea of the mathematical discourse, the posing purposeful questions, and eliciting eliciting and using evidence of student thinking. So when we're creating teams, we do have to think about the size of our team. Now, given that we are talking about high school, we're talking grade 3 and up, if we're looking at what Peter suggests in the book, Building a Mathematics Classroom, he would suggest teams of 3 or more. Teams of 3, sorry. The reason he suggests a team of 3 is because we want to avoid redundancy. We want new ideas, new experiences, new interests, new languages being expressed by the students. We want diversity also. So we want students that are going to share different ideas, different viewpoints, different perspectives, different representations of what is being seen in mathematics. If we go with teams of 2, what we end up with is basically a back and forth discussion. We want to have an exchange between our students, which is why we want at least 3 students involved. Some teachers might be afraid of doing random groups, but there are benefits to doing it. For example, it'll increase the thinking. It'll create a willingness to collaborate amongst your peers. It will eliminate social barriers. It'll increase knowledge mobility. It'll increase enthusiasm for mathematical learning, and it'll reduce social stress. You might be wondering, how is that even possible? Well, let's imagine a student who has difficulty making friends in the classroom. By putting them in a random group, it forces them to exchange with others, and they might destroy a social barrier that was already there, and they might make new friends. Or perhaps you have students, young boys, who only like to work with the young boys. Well, by putting them, they might see, hey, the girls have some great mathematical ideas too. Let's see what we can learn from them. A student with social anxiety who is struggling in mathematics, who's having difficulty expressing themselves. Well, if we put them in a random group once in a while, I'm not saying every single day, but once in a while, that student might feel a positive reinforcement when the other students say, hey, your idea makes sense. That's awesome. I love the way you're representing the problem. So Peter actually recommends 14 different practices to build our thinking classroom. Now, obviously, we cannot implement all 14 of these practices in one shot. It would be too much for our students. It would be too overwhelming. So that there are 4 bubbles here. So these 4 bubbles grouped together the 14 practices in different groups where we can start doing it together. So for example, give students thinking tasks. So I've started giving students problems of the week. Frequently form visibly random groups. Use non-vertical permanent surfaces. Those are the first ones. Then we go into the second aspect, defronting the classroom, which I'll talk about in a few moments. Answer only keep thinking questions. Give thinking tasks early, standing and verbally. Give check your understanding questions, mobilize knowledge, etc. There are many practices here being suggested. I would never suggest to do them all in one shot. Do them progressively, slowly. Be careful. You don't want to cause a struggle for your students. When we're talking about collaborative thinking and the productive struggle community, some teachers are going to prefer having roles assigned to their teams. So some teachers might say, well, I want to have a little bit more control over my group. So in my group, I'm going to have one animator or mediator. So this will be the person that will direct the activity if you want. Then you'll have the timekeeper, and then you'll have the note taker. And these roles should change over time. Do not stagnate the same role on the same student all the time. Make sure you alternate. Make sure that every student gets to try every role to figure out what works for them best. In this, we want to encourage collaborative thinking, which means that we want to ensure that there's a structure to encourage students to engage with others' ideas. We want to use, for example, a placemat structure. Now, you might be wondering, what is a placemat structure? And that's actually coming up a little bit later in the presentation. You will see an example of that, and you will get how to use that in your classroom. Continuing onwards with the idea of productive struggle community. Your classroom is a community with individual mathematical ideas. Your students. Your students are going to be encouraged to work with partners, to share their ideas, to take turns listening, to encourage of others. They're going to be sharing ideas. We want them to value each other's ideas. They're going to make mistakes occasionally, and we want them to recognize that they can learn from their mistakes. We don't want one student dominating the group. We want people to take risks. We want everybody to have a voice in the group. For this to happen, there has to be an atmosphere of respect. There has to be a respectful attitude amongst the students, amongst the others, amongst the people working together, and the community as a whole. Students need to understand when they're working in a productive struggle community that yes, it does happen that we will get stuck, but there are means of getting out of it. There are strategies that we can use to apply to get out of this rut that we might be in. Earlier, I mentioned that one of the strategies proposed by Peter Legel is to defront your classroom. Now, what does that mean? The traditional classroom, we could actually see it up here on the right top corner. Basically, all the students' desks are aligned perfectly. They're all facing towards the teacher. The teacher is leading the classroom, a little bit like I'm doing today. The teacher is doing all the talking. Although this might have worked traditionally, this is not the optimum format that we would want today to have a thinking classroom. To have a thinking classroom, we want to engage our students in mathematical discourse. To do that, we need to defront the classroom, which means we need to set up teams, as you can see over here on the upper right corner. So we want the students to be randomly set a little bit in the classroom. Again, they know where they're going to sit, but it's not a traditional layout. With this format, the students are going to collaborate more. The teacher is going to talk a little bit less. The teacher becomes a facilitator at that point, rather than the pure classroom leader. When we set the tables up in a different way, it really sends a message to the student as to what's expected, as to what's going to happen in the classroom, as to how we hope our students are going to collaborate together. In fact, the placement will often shape the teacher's intentions. And you can see over here on the bottom picture, there is a lovely, ginormous classroom that is shown. And it is defronted. The students are set up in teams. They can work together. The teacher is not necessarily always at the front of the class. The teacher will walk between the tables and go help out the students as they need it. When we're talking about thinking routines, the notice and wonder activities, they come from the National Council of Teachers of Mathematics. So we can find this on their website. Now, there is one little ick. You do have to have an account with the NCTM to be able to access these. There's a cost associated to that. I'm not going to deny it, but it is worthwhile. What you will get with the notice and wonder activities is different lesson plans for your students. So you'll see there are lesson plans for K4 to K4, K5 up to grade 2, grade 3 and 5, grade 6 and 8, and grade 9 and 12. So for example, over here on the right, you could see some of the lesson plans available for grades 9 to 12. Detail, you probably wonder what is included in these lesson plans. Well, first and foremost, we have our visual prompt. Now, in this case, if we look at this visual prompt, ask ourselves, well, what do we notice? What do we wonder? One student might say, I notice all the windows in the background. Great observation. Excellent. Another student might say, I noticed that there's fountains and there's water coming out of it. Excellent. Perhaps one student might wonder, well, what shape is the water going in? Now we're getting a little more interesting, which might lead to a mathematical question eventually of, well, can we calculate an equation for that curve that's being drawn by the water? There are other elements included. So with the PowerPoint that you get that has the visual prompt, you have one slide where you can write on your smartboard the observations that the students make and the wonderments that they have. So you can actually collect the best answers from your students and put them on the board. Praise them, positive reinforcement. Then there's a second slide that's also included, which is what type of math questions could we ask about this lovely image? So again, we had what do we notice? We notice the windows, we notice the fountains, we notice the trees. It's a beautiful sunny day. All these are great things that you could observe. What do you wonder? Well, we wonder, in this case, for example, what curve is represented by the water in the fountain. We wonder what is the area of the windows. We wonder what is the height of the pole in the background, for example. What type of math questions could we ask? What is the mathematical equation that defines the parabola seen from the water fountain? That could be a very interesting question. How do we calculate the area of all the windows in the background? Could we guesstimate it, potentially based on references that we have in the picture using perspective? Maybe. There's different questions like that that we can ask ourselves. There's even more included in the notice and wonder activities. Notably, you have a lesson plan, and the lesson plan is wonderful because it gives you the grade band. So in this case, they're told that it's grade 10 to 12. We're told the content that's going to be seen in it. So in this case, application with conics, parabolas, circles, hyperbolas. We're told the vocabulary that's expected of students. And we'll see also that there are questions. So there's an answer key over here as to what type of responses we might expect from our students. There's also a document for the students to complete. Earlier, I mentioned the idea of the placemat structure to encourage that critical thinking. So when we have that visual prompt on the board, what do you notice? What do you wonder? Each step up. Well, let's put the students together and let's have them work on a placemat. So in this case, the placemat has 3 spaces for the students to work on. Student A, in this case, noticed that the windows at the top floor appear to be congruent. Great, he's got excellent mathematical language. Love it. Student B noticed that the base of the fountains are wavy. Student C noticed that the water flow out of the fountain seemed to be shaped like a parabola. Excellent. Then we get them to collaborate together, gather what they notice together and put it in the middle. So for example, in this case, we notice that there are curves and parabolas. Excellent. Then we get them to write their individual wonderments on this page. Then we get them to write their individual questions, and then we add their collaboration together in the center of the page. Now, obviously, we're not going to do this on an 8.5 by 11 sheet. We want this on a bigger sheet so that the students have room to work, they have room to write. Continuing onward, we can see the lovely parabola over there. We can actually outline it for students to make it a little more obvious for those that didn't see it. Now, obviously, we need to be careful to align the Notice and Wonder activities with the Quebec education program, notably the progression of learning. In this case, happen to be well aligned with the grade level, which would be grade 11 in this case, and it would be an end of the year activity because usually the conics we see it near the end of the year. Some of the activities over here that would be included with the Notice and Wonder activity in question. Now, if we look at the progression of learning, what we see right away is describes and represents and constructs geometric loci in the Euclidean and Cartesian planes with or without technological tools. We see analyzes models, suggest model situations involving geometric loci and the Euclidean and Cartesian plane. We see and model situations using conics, and that's where it gets interesting here because now we're describing the elements of a conic, the radius, the axis, the directress, the vertex, the foci, etc. We're graphing conics, so we're starting to graph it within a graph, and you can see the graph forming over here. We're adding our reference plane. We're constructing the rule, which is indeed what we're doing over here with the equation. We are finding the rule, for example, in the standard form. We're validating and interpreting the solution. So we're making sure that it makes sense. We're checking that, the points on a parabola will correspond to the equation we developed. So you can see in this case that the activity does align very well with the QEP and the progression of learning. In this case, they said rewrite the equation in vertex form. Be careful, the way that the questions are formulated might not be the standard way that they're formulated here in Quebec. So you might have a little tiny bit of work where you're rearranging some of the text. Garfield Jean Newman also suggests that we look at peer assessment in collaborative learning. This is really important because students need continuous feedback, and not just from the teacher, from themselves, from other students. They will learn from that. Now, this is perhaps one of the biggest faults of the Notice and Wonder activities because they do not have this peer assessment involved in them, but you can easily create them. And in this case, for example, we have a scale of 1 to 5. So are the students willing to reconsider their positions? Well, let's say little Timmy was at a 4. Okay, cool. Little Jerome was very, fixed on his ideas. We'll put him at 1. Unfortunately for today, he wasn't at his best. But that way they can learn from the experience, they can adapt to the experience, and they can then progress and become better in the future. Are they willing to defend their opinions, or do they just submit to the ideas of the others? Are they respectful of people who disagree? Do they challenge in a responsible way? Because it's important to challenge your peers occasionally. Not everybody is going to have the right answer, and that's okay. We learn from that. We establishing a consensus also amongst the team members. Now, as I mentioned, the Notice and Wonder activities from the NCTM, unfortunately, they're designed in the United States of America. So sometimes it's better for us to design our own Notice and Wonder activities, which is what I did over here. So I decided to use a very unique piece of architecture here in Montreal, which is l'Îlot Balmoral, a building designed by a Canadian architecture firm. So the building can actually be found here in Montreal at the Quartier des Spectacles, so near Place des Arts. It houses right now the National Film Board of Canada, part of l'Université du Québec à Chicoutimi, l'École des Arts numériques et de l'animation et du design. It's actually a really cool building, as you can see right here on the right. I mean, you might ask your students, what do you notice about the building? What do you see? And obviously they're going to say, well, we see red, it's beautiful, we see white, we see lots of windows. Some students might say, well, we see angles, we see lines. Oh, now we're getting interesting. You show a different picture, a different angle of the building to the students. What do you notice? And again, some students might say, well, we notice the lines, we notice the colors, we notice the windows. All these things are fine. And again, we ask them, what do you wonder about it? Well, maybe it might help if we give them a picture. We've gone from concrete to pictorial at this point. So by giving them a picture of the side view of the building, the two lines intersecting might become a little more obvious for the students. And in fact, you'll see the two lines shown right over here. and how they're intersecting together. Now we're starting to cook, because now we're going into sec-free mathematics. And in fact, that was my goal with this exercise. So now we might ask the students, well, what is the coordinates of the points of intersection? To get coordinates, well, we're going to need a reference plane. So now we need to add our reference plane, that is to say our Cartesian plane, to the picture that we had over here. And here what I did, because we have a scale that's mentioned down over here at the bottom, that says we go from 0 to 5 meters, well, I was able to deduce then that my first point over here is exactly 10 meters away to the right, 5 meters vertical. The point over here, I was able to determine that is exactly 35 meters to the right, because it is 7 jumps to the right, 7 times 5. It is at 0 elevation because based on my reference plane, it is on the x-axis, the abscissas. We have other points that we can also use. So now we have 2 lines and 2 points on each line. Well, I wonder if we're going to be able to use that to our advantage to be able to figure out equations of the lines. So we go into Desmos. We create a graphic. So now we've gone from concrete to pictorial to a little more abstract. And it's important that the students see the abstract. What you'll notice in this case is that the 2 dots over here on the right, so the point minus 1045 and the point minus 525, are not directly touching the line. We can do a visual demonstration with Desmos for our students. In Desmos, you can actually adjust your coordinates. So if you notice over here, I'm moving the dot on the line, and I got exactly minus 1047. Same thing for the point that's a little bit lower. I'm going to line it up. So here I'm at minus 4 point something. Oh, minus 5 and 27. So the minus 5 corresponds to the minus 5 I had in the previous slide. So that means those are the coordinates I'm interested in. Well, now that I have 2 lines and 2 points on each line that are definite, that are assuredly there, can we find the equation of those lines? And the answer is yes. We can use a little bit of analytical geometry to get there. Okay, so we have the first 2 points of line A. What could we find with that? Well, we could find the equation of a line, y equals mx plus b. Or if you prefer, y equals ax plus k, or y equals mx plus k. Depending on the format that you want to use, there's different formats. Okay, so in this case, we ask our students, well, what do you notice about this equation? Oh, there's 2 variables. Okay, great. So which one is your independent variable? Which one is your dependent variable? Oh, x is my independent, or, they'll answer the questions as you go along. What does m represent? At that point, you hope they'll tell you the slope. Okay, great. The slope, excellent. How do we calculate it? Well, we do the difference in y's over the difference in x's. I'm not going to go over the details right now of this, but basically we get a slope of minus 4, which makes sense for the red line because it is decreasing. It's going down towards hell. From there, we can find the line equation. So we can find the y-intercept, which is b. To find the y-intercept, we use a point that is directly on our line. And in this case, I use the point minus 10 and 47, and we place it directly in the equation. So now on the board, we have a beautiful example for our students, a model that they could use to find the equation of line CD. That is to say, the green line. Again, I'm not going to go over all the details now, but basically, through a little bit of modeling, your students could eventually get line CD by doing the same process. Wonderful. Now we have 2 line equations. I wonder if with those 2 line equations, we could find the coordinates of the point of intersection. The answer is yes, we could. And there's several ways that we could do it. But remember, in this case, I said this was a Sec 3 problem, so a grade 9 problem, which means that there's really only one way that we teach the students in grade 9, which is the method of comparison. So what does the method of comparison involve? It involves comparing our first line to our second line. So we basically recognize that the y-intercepts are going to be the same. So we're going to say y1 equals y2, which is to say that minus 4x plus 7 is equal to minus 0.2x plus 7. And from there, we're going to solve the equation using a little bit of algebra. Again, we can teach our students the balance method, depending on how you want to go about it. At this point, they should have some understanding of that. And eventually, we solve for x, and bada bing, bada boom, it gave us 0. Okay, well, how do we solve for y? So at this point, our students replace the value of x in the equation, and they find our value of y. Excellent. How do we validate our answer? Well, we take both our value of x and y, we replace them both in the equation, and hypothetically, it should give us an inequality. And if it does give us an equality, and at that point, why not have a little bit of positive reinforcement? Why not do a drawing to reinforce the fact that we did good? Continuing on, we've got now our point of intersection, which I've called I, and we can establish a conclusion. And all this came from that activity of noticing and wondering. A little bit of modeling was involved in there too, but we didn't give the student the answer. We led the student, we facilitated their learning, and we helped them in their learning. Further, so for example, let's say we want the total height represented by the yellow line that you see in the two images, both in the concrete picture on the bottom and the pictorial image that you see on the upper left. Well, for that, we're going to have to be intuitive. So in this case, we technically already have the blue height that you see represented over here, because we're going from 0 to, we already have the purple height over here. We just found that a couple of instances ago. We know the orange height over here, so the 10 to the 5. So we know that that's 5 meters. What we want is the little blue area, so the little blue line over here, we need that height there. So the question becomes, how do we figure that out? Well, to figure that out, we know that the total height will be 7, which was our previous height that we found, plus 5, which is the yellow height that's there, plus the height of the blue section. So to do that, to find the height of the blue section, we take our line equation again. And in this case, it's the line equation, I think it was line CV. And we replace a point that we know, which is a point 30 in this case, so x equals 30. And what that gives us is 1 meter. Now, why did I use 30? It's because I went 6 jumps forward with my scale of 5 meters. So now I can figure out the total height by just adding 7 plus 5 plus 1. Great, it's 13 meters high. So now you have a real life application that is actually pertinent to the students. And in fact, if you want to push it to a field trip, you can even bring the students to the building, bring a ruler, measure it out. Maybe they'll see that it is actually 13 meters or close. That might be a challenge, but could be fun. Going a little bit further with the notice and wonder activities, you'll notice I've talked about concrete, pictorial, and abstract. This is the CPA approach. So concrete was the actual building itself, bringing the students to the building, letting them see the building, also letting them see the pictures of the building. The pictorial was when we went with the reference plane, and also using Desmos is considered pictorial to a point. It's more abstract, but it is still pictorial. Continue onward, we went to algebra, which was basically, we went to the abstract, which was basically the algebraic approach to determine the line equations, to find the point of intersection, to solve the system of linear equations. There are other approaches that we can use also. We do want our students to do many different representations. For example, visual, symmetric, verbal, contextual, physical. And we need our students to remember that this is a non-linear process. We need our teachers to remember this too. So although one student might be able to physically show you something with manipulatives, perhaps they're not yet ready to show you visually with a drawing what they're representing. Perhaps a student is able to represent symbolically how to solve a system of equations, but they can't verbally express it to you. They can't tell you how they did it. Well, we need them to make those connections. We need to help them make those connections. And through the notice and wonder thinking activities, we can get them there. On with the Ilo-Balmoral example, we can look at Pythagoras. So again, if we give the students this image over here, we ask them, what do they notice and what do they wonder? Well, we would hope that they notice the right angle triangle that is represented in green, purple, and red to your left. This is contextual. Then we bring them to pictorial. So now we have our same triangle, represented in the Cartesian plane that you see over here. From there, we continue onward and we go to physical because some of our students need to touch it, need to do it with a manipulative. So at that point, we can make them cut it out. Then we can go verbal. Okay, well, we're talking about Pythagoras, which means that we're going to use the hypotenuse squared, which is equal to the base squared plus the height squared. Now, these are a lot of words. A lot of students might get lost in that, so we then go symbolic. And we say, well, the formula is going to be c squared is equal to a squared plus b squared. And then we replace our numerical values in there, and we find, finally, the value of the hypotenuse. Wow. A quick example of notice and wonder activities that you could create for your students. Using a little bit of graphy that could potentially interest them. So looking at geodesics. So in this case, a geodesic is basically a line or a curve that represents the shortest route between 2 points on Earth. Now, in a standard two-dimensional plane, you would be say, well, it's going to be the red line, obviously the shortest path. In the real world, it's important to explain this to the students because the Earth is a curved three-dimensional sphere, the shorter path is actually the purple curve. But I'm going to be honest, I'm more interested in the line in this case, and we're going to do a little more analytical geometry with that line. So we notice that there are distances that we can travel, right? And perhaps we might be curious as to what the line might represent in terms of distance, so distance between 2 points. We might be wondering what is the midpoint of that line that we had earlier. Well, we can approximate it. We can approximate that it would be about here, very close to Lake Superior. Okay, let's put it on a reference plane, which means now we have a Cartesian plane, which gives us exact points. Notice, however, Winnipeg is directly in between 2 points. Now, that could be a problem. Well, let's use Desmos to our advantage to figure out, for example, the midpoint of those 2 points. So what you're going to notice is I labeled my points. I have point O, which is the origin, 0, 0. Point A and point B, which are the 2 points that we have over here, which were the points in between Winnipeg or around Winnipeg. I want to find the midpoint. So in this case, I decided to do the midpoint function in Desmos, so the midpoint between points A and B, and it gave me a coordinate. So the midpoint over here is minus 1750 and 500. Great. So now I want to know the total distance between my origin, which was Montreal, and Winnipeg, which is that midpoint that I just established. So what I did now is I established basically my distance by doing the distance formula in Desmos. So I did the distance of 0.00 all the way up to the point minus 1750 and 500, which gave me a total distance of 1,820 units with some decimals there. I'm not going to go into the whole decimals. Now, perhaps I want to know the line equation also. Well, I could figure that out also using Desmos because I have 2 points that I can use to find the slope. I could find then the midpoint also, in this case, the midpoint between Montreal and Winnipeg, which was minus 875 and 250. Now, this is really interesting for your students. It can be used as a tool to validate their answers that they do in class when they do the calculations. We could potentially use Desmos is for projects. So for example, over here, this is a project that was done at the Collège Français d'Ongueuil, where a Sec 5 teacher asked their students to create a Cat Cafe logo using Desmos and using all the functions that they learned throughout the school year. So what we can see, for example, if we look over here, is we have a parabola that's shown. We have, for example, over here, function that goes to the power of x cubed. We have also functions for example, circles over here that are defined too. All these are different projects that you can do with your students. Now, as we mentioned, it is interesting to look at Desmos a little bit. I'm just going to escape and go back to the previous slide. I apologize for that. So we do want to go into Desmos a little bit and look at it and see how to use it. So if we go into Desmos, and hopefully this will work. Perfect. We want to see how we can use this with our students. So let's say we want to look at a function. Let's say a line function, y equals mx plus b. Well, we'll notice that in Desmos, we can add sliders. So let's add them all. Now, let's say I want to see what the purpose of the slope is, what it does. I can activate the
Can you
animation.
reshare? Sorry, can you reshare your screen? It's just we're seeing your presentation and not Desmos.
Sorry, my bad. I will escape the presentation. Give me a second. It's not because I'm finished with the presentation anyways, so give me a second. All right, let's reshare this. Sorry. Desmos. Boom. You should see it now. Do you see it now?
Yep, all good.
Perfect. Thank you very much. I appreciate that. So as I was mentioning, I put the line equation into the box that you see over here on the left, and I kept it very general. I kept it with the parameters m and b in this case, so the slope and the y-intercept. And in this case, I asked it to add sliders. So if I add the slider for m, we can see the effect that slope has on the line. Now, this is going super fast. So we might want to adjust the properties a little bit. So we might want to adjust the speed, slow it down a little bit. And then our students will get a better idea of what's happening. So now this might be a little bit too slow. Yeah, this is a little bit too slow. Let's go a little bit faster. There we go. So now the student can start seeing what happens because of the slope. If we stop that here, let's say, and let's say we want to see what happens with the y-intercept now. Again, we can adjust our slider, and it shows us what happens with the y-intercept. This functionality within Desmos is super important, especially when you get to Sec 4 and Sec 5, and you start looking at the 4 parameters. So for example, let's say we're looking at a quadratic formula. So y equals a x minus h to the power of 2. This way, will be power of 2 and plus k. So here we have 3 of our 4 parameters, a, b, h, and k. And we want our students to realize what happens with these parameters. So let's say we start with parameter a. Again, we're going to reduce the speed of the function as it moves. And we're going to go input. So now we can see the line that is there, and we are going to go put in the slider. Get rid of this and that. Sorry. Oh. Okay, so we have our line there. What we're going to see is when we adjust A, we adjust the horizontal width of the parabola, which is very interesting to see. The students see it immediately. We also see that when A is negative, the parabola is facing downward, it's concave down. Whereas when A is positive, it is concave up. We could also move parameter H. So if we want to move parameter H in this case, we'll reduce the speed again a little bit. So parameter H, what we're going to see is it's a translation to either the right if the number is positive, or it could be a translation to the left depending on what the numbers are. You can do the same thing with K. We can do a translation in this case that will become vertical, and eventually a translation that will go downward into negatives also. And again, we can ask our students as we're showing this to them, what do you notice? What do you wonder? We don't give them the answers right away. We lead them to the answers, we facilitate their learning, but we don't give it to them. The beauty of Desmos is that we can do this with all the functions that the students are going to learn throughout the school year. So for example, let's say we wanted a sine function. So I could put f of x equals a sine b h plus k. So now we have all 4 parameters being shown. Great. Well, in this case, we're going to add our sliders and we'll see what happens with each one. So once again, if we look at A, and again, reduce the speed for the students so they can actually see it, we put it in and we can see that in this case, A is basically pulling it vertically or squeezing it, compressing it. We can also play with B. So again, we change the speed and then we put it at 0.02, for example, and we upload it. And what we can see is we're doing a horizontal compression or dilation where we're pulling it apart. Again, same idea with H and K. We can again look at what the different parameters are going to do. Now, doing functions is not the only thing that you can do in Desmos. There's so much that we can do in it. You saw a little bit of it earlier when I was doing, for example, my line equation. I was looking at the distance between 2 points. So for example, if I have y equals 5x plus 6, right away my line is drawn. What's interesting here is that I can go see the x-intercept. So in this case, minus 1.2 and 0. I can go see the y-intercept, which is which is a little bit higher up over here, 0 and 6. So then I could define these points on my line potentially. So I could, for example, say the point A is going to be the point 1.2 and 0. It should define it. Slider. I don't know why it's adding a slider. Label, that's it. Okay, label. Boom. And also add, for example, our point B. So point B was, I don't remember what it was exactly. It was 6 and 0. So 0 and 6. So we add point B, we add the label, boom, done. Then from there, we can start looking at the distance between the 2 points. So if we want the distance between point A and B, we can write distance equals, actually, I think it was distance A comma B equals, is it like that? No. I'd have to relook at how to do distance formulas, but we can easily do distance in Desmos. I apologize for not doing it correctly right there. In fact, it's giving me a pointer over here. Sometimes here. Okay. So I'm just inputting it the wrong way, but there's ways to do the distance between the points. You get your students to draw different figures in Desmos also. For example, rectangles, squares, rhombuses, any different shape could be potentially drawn in Desmos. You could get your students to be creative and do a project like the Cat Cafe logo that we saw earlier. There is so much that we can do with Desmos. It is well worth your time to take the time, play with it a little bit, get to learn it. Now, I notice that we have a comment in the chat, and it's great that you can use this resource for free and without logging in. I absolutely 100% agree. This is an excellent resource that should be used in all high schools, and it is something that is easy to use and it's free to use also. At this point, there's about 10 minutes left to the program. If there are questions, curiosities, wonderments, whatever it might be, please feel free to ask, whether it be in the chat, whether it be, expressing yourselves outright. If you have a question, please ask it. I am there to answer your questions. I love to know what you want to know about these notice and wonder activities, the idea of critical thinking in the classroom, and how we can apply it in the future. Excellent. I see somebody saying fantastic. Love it. And I'm waiting for your questions. I just want to know what your thoughts are and if you do have any questions about this. Yes, Michael.
Hi, Alex, this is so cool.
You.
And very thorough too. A lot of stuff that I hadn't seen, and I'm happy that I came. My question is, as the teacher,
Yeah.
I noticed those lesson plans that you showed us had a full list of the mathematical concepts that you're going to hit in these notice and wonders. But that felt like a lot to have in your head at once as the teacher. So do you need to have real mastery of everything that's there? every thread that your students might pull that they might wonder about? Or is it okay going in knowing you're going to leave some of those on the table and like not have answers for them?
In all honesty, we're all human, right? We all learn from our mistakes and we don't know everything, right? So it could happen sometimes that you will have some little lapses of knowledge. You might not know exactly what to answer your student, and that's okay. It does happen. When that does happen, you just tell your student, look, that's a brilliant question. I'll look into it and back to you a little bit later.
Is the spirit of it that when your students wonder something, you're meant to answer that, or no?
You're meant to encourage the wonderment. So you're meant to basically use a lot of positive reinforcement to make them say, wow, look, you're being curious, you're discussing it. Let's look at the math behind it also. And if you look at the progression of learning, all the math that we had in that first example is there. Now, that was like grade 11 math, I'm going to be honest, and that's end of the year math. And like I said, the notice and wonder activities is something that you have to do on a semi-regular basis to get that fluidity going with your students, right? To get them working a little bit quicker, a little bit more at ease. At first, when you start off doing these notice and wonder activities, it will be destabilizing for your students. They're not going to be accustomed to it. And you have to tell them, look, it's a process. We're going to try it once, see how it goes. We'll make adjustments for the next time. And then you build on that. It's a foundation. And once students develop that trust, not only in you, but amongst their peers, it's going to go so well.
Thanks.
Very welcome.
So it's investment worth it. It's worthwhile investment, you're saying, Alex.
Absolutely, 200% certainty.
Cool.
And I noticed, Chris, that you put a link in the chat.
Yeah, well, we have a bunch of tutorials on Desmos as well. I was going to ask you, like, where do you learn about Desmos? Like, I know just playing around with it and stuff, but
yeah, I mean, for me, it was really trial and error that I learned it by. But as you mentioned, the resources that you're showing over there with the link is actually a great way to learn about it. I've done a couple of webinars with Amplify, which actually looks into Desmos and also into different aspects of it, because there are activities associated with Desmos also that you can use with your students to get them again noticing and wondering and answering and being active in their learning, which is ultimately what we want to do. We want to engage the students. If the students are not engaged, they're not learning. They're passive, laying on their desk, unresponsive. Okay, it might be because of external reasons. Maybe they didn't sleep all night because the news is stressing them out like crazy. Maybe there's problems in the family. You don't know as a teacher. But ultimately, if you can get your students engaged, if you can get them talking about math, if you can get them interested in math, win, win. Develop that conceptual understanding, which will turn into procedural fluency. And as a teacher, you will become more flexible and more adept at seeing their answers in different ways. And in fact, when I was doing my example of the notice and wonder activity with the intersecting lines, and I found the point of intersection, some students might have been brilliant and said, well, sir, you had the answer on the graph all the way at the beginning. And yes, that is true. I did have it there. That is a pictorial representation of the answer. But I wanted the abstract version, the symbolic version of it, because I wanted you to make connections. Again, you encourage, you give that positive reinforcement. You never put a student down in their learnings, and you bring them a little bit of joy in mathematics, because everybody can do mathematics.
right. No, that's great. And I like too that you're putting at this forefront that it takes time to establish these routines, like routines take a bit of time and it might not feel great the first, second, or even third time. But
absolutely, it does take a little bit of time, a little bit of investment, but once you get there, the benefits are 100% there.
right.
And it might make us uncomfortable at first. That's normal. We have to get out of our comfort zones to make our students learn. We have to get our students thinking. I'll give you an example. I showed some conceptual circles to some teachers today, and it was the first time that they saw it being applied in a problem. They all found the idea very interesting. They're worried at how the students might react to it, but they're very aware that if they show conceptual if they show conceptual circles to their students, progressively, students will be familiar with it, and then they'll be able to handle no problem. So again, it's that investment, and then they're able to learn from it.
Mm-hmm. Yep. And I think too, like Peter Liljedahl, for example, who does the thinking classroom, mathematic thinking classroom, has great also tips on how to like start creating that environment for learning. And that's where it all focuses back to, right? It's all about the learning and the conversations that happen and the exchanges that happen. But he also mentions it does take time.
Yes, absolutely. Now, I noticed that Melissa has a question. She said, how do you implement peer feedback to ensure that they are being honest and respectful? Well, as a teacher, we do have to be there supporting our students, right? So we have to walk around the classroom. We're not just going to sit at our desk looking at our students. We have to walk around, we have to listen, we have to observe. If we use some of what Peter is saying, basically using the vertical non-permanent surfaces, well, then we can have our students working in teams together on basically a whiteboard, essentially. They can write down their answers. They can actually look at what their peers are doing also without necessarily copying, thinking about what they did. Pass by as a teacher, and you can put by some feedback for your students also in a different colored pen without necessarily giving them the answer. And again, amongst the peers, to ensure that they're being honest and respectful, well, that has to come from you partially too, because you have to enforce those as values in your classroom that you want your students to adhere to. One of the first things I tell my students every single school year, the most important word in my classroom is respect. You respect me when I'm talking, stay quiet. When other students have a question, you raise your hand, you let them speak, and then you respond afterwards if you have that permission. You respect your environment in the sense that you don't draw on your desk, you don't draw on the walls, you respect, and you be honest with each other also. If there's a mistake happening, feel free to outline the mistake, but be respectful about it. Hey, little Johnny, I noticed that your answer is different than mine. I noticed that you didn't put that 5 when we were solving the problem. Why didn't you use the 5? Well, see there, that's a constructive critique, right? So now the student might look back on their problem, might review their problem, and might find a solution. Or the other student might say, well, finally, I didn't need the 5. It didn't lead me anywhere in the answer. So it leads again to that idea of discourse between the students. It's honest, it's respectful, and there's that tact we want between the students. It's something that we have to model for them also. It's not something that intuitively will come naturally to them. We have to show them how to have these conversations. And we can't just expect it to come naturally for them.
Interesting.
Answers your question, Melissa.
Yes. Well, thanks for your questions, people. We've come to our close. Alex, thanks so much. That was really cool. I love Desmos too. Like, I love seeing you manipulate the tool, and it really gives that visual aspect that I think our kids need. So that's cool. And Mark was saying too, like we should start implementing these engaging activities for our kids. Absolutely. And if you guys need some more support, you can reach out to Learn. There's tons of resources out there, or we can point you to some. We will be sharing out this recording with the presentation and the video for all those that want it. Please share it out too. It's available for free for everyone. And again, I want to thank you guys for taking some time and joining us. And Alex, again, thanks so much for taking some time and sharing some of these interesting ideas and thoughts with us with this math.
My pleasure.
I wish you all a great evening, and check out our calendar. We got lots more events coming up this year. Always great to have people involved. So thank you.